Good day two. Let's keep going with the stoichiometry. But first we need to balance this. Let me copy this. Might need a little more room. Alright, if you haven't balanced this, might want to pause the video and try it again. These stoichiometry problems don't work well without a balanced equation. Alright, iron, oxygen. Actually I'm going to put the oxygens together. Alright, they appear two different places, so they each get their own line now. Kind of putting them side by side on this side. Alright. Alright, I'm going to do iron last because it's all by itself. It's the most easily manipulated. Oh wait, hold on. We gotta count this up. 2, 1 carbon, 3 from the iron oxide, and 1 from the carbon monoxide. Over here to the right, we have 1 iron, 1 carbon, and 2 oxygens. Alright, like I said, we'll do iron last. Carbons only appear once on each side, so whatever I do to that coefficient it has to match that. Those two coefficients have to match because of carbon. Alright, so let's do the oxygens. Let's do the oxygens first. What if we put a 2 there? Because there's 4 on the left side. Alright, so if we put a 2 there to get 4 oxygens on both sides. Alright, that's already going to change up one of these oxygens. So, alright, let's just see what happens. We need to update that carbon as well. And therefore we need to update this carbon to also get 2. That's going to update this oxygen, and that's going to give us an even number, an odd number on the left side. That's not good. Okay. This is 5. All right, we need to get this to be an even number. So let's just turn that into a 3. Ping pong. Sometimes you got to do trial and error. All right, let's try 3. So this is going to be 3, 2 on the left side. We'll do that later. All right, let's put a 3 there. Update this one also by 3. We got 6. Let's go over here and make that a 3. All right, that's going to update that oxygen. Let's do that. All right. Again, the reason we did that is to get these two sets of oxygen to be an even number, and that turns out that they match up. Now that's easy because this iron is all by itself. We can make that whatever number we want. Put a 2 there. All right, the coefficients are 1, 3, 2, and 3. It was not an easy one. All right, let's answer this question. We got 84.8 grams of iron 3 oxide. It's going to react with excess. That means there's more than enough. Right, so we don't have to worry about the carbon monoxide. Although if you're around it, you should worry about it, but not in this stoic problem because there's more than enough of that. So it's already telling you this is the limiting reagent or the limiting reactant. The iron oxide is. All right. So iron is produced. Okay. What is the theoretical yield? Well, remember the limiting reagent leads to the theoretical yield. So far, we're just going to use the number given, all right, 84.8, and see what we get. That's a lot of verbiage for something we would do anyway. So let's do it. 84.8. Here, let's just make sure that's the right number. Grams of iron 3 oxide. All right, first step, if we're not given moles, is to convert to moles. So, okay, we need our periodic table. All right, let's just set the units up. All right, this here is from the periodic table. We're going to need the molar mass. All right, iron and oxygen. So let's get 4 digits. Iron is right there, 55.85. Let's go with 55.85. 55.85 times 2. Okay. 111.7, and oxygen is 16.00 times 3 is 48. 159.7 grams per mole. All right, so we need to plug that in, the molar mass down here. I should not have put that question mark. All right, get my blue pen back. 159.7. All right. Second step is the mole ratio, where we're going to turn the iron oxide, the given information about the given substance. All right, they gave us information about the given substance, and so this is where we turn it into the substance that we desire, which is iron. So that's why we balanced, well, that's not why we balanced the equation, but we get that information from the balanced equation coefficient. So it's a 1 to 2 ratio. That's what we're going to use. All right, 1 to 2 ratio. Just too many colors. 1 to 2 ratio. Those units cancel out, top and bottom. All right, our final step is to convert to the desired unit, because now we have the desired substance. Now, but the question is asking, what is the question asking? What is a theoretical yield? So it doesn't specify, but I can see ahead that we're going to need grams anyway to do the percent yield, so let's just do that. All right, I think that's what they meant. Find the number of the mass. All right, so let's convert that to mass, iron. Okay, so we got that earlier, right here. It's the molar mass of iron. One iron. So that's what we'll use. 1 mole of iron has a mass of 55.85 grams. All right, cancel these out. All right, let's punch these numbers in. $84.8 divided by 159.7 times 2 times 55.85. All right, 59.3. We'll get 3 sig figs because the given measurement is has 3 sig figs, and the only unit we have left is grams of iron. So there's an answer to part A. The second part of this is we haven't used red. is what is a percent yield? Percent yield, right? They give us 58.2 of actual. Right, so percent yield is percent yield is the actual amount that was made over the theoretical is the total possible, which is what we just calculated. So this is your theoretical. All right, you get that by doing stoichiometry with the limiting reagent, which is what was given. All right, so you do actual over theoretical, and you multiply that by 100 to turn that into a percent. So let's do that. All right, what did it say? Actual was 58.2 grams. All right, 58.2 grams, and then the theoretical is what we calculated right here in blue. That's the possible maximum. All right. All right, I want to round to 3 sig figs, 98.1. Well, that's really close to rounding up. Because I used a rounded number here, it might, I think I'm gonna say, well, this is good enough. It might round up to 98.2 if we didn't round. All right.